Welcome to The Explainer. So today we're going to tackle two of the biggest problems in modern tech. First, what do you do when your dataset is just so huge it can't possibly fit on one computer? And second, how do you store all that data without completely breaking the bank?
Anyone who works with data, especially if you're pushing past what a traditional database can do, you eventually smack right into this wall. So what's the game plan when a single machine just can't cut it anymore?
For the longest time, the answer was pretty simple. Just, get a bigger, beefier computer. But the datasets we're dealing with today, from web search indexes to entire genomic sequences, have completely outgrown that strategy. We are talking about a scale of data that demands a whole new way of thinking.
And this quote, wow, it just lays out the brutal reality of the situation. When you're operating at a massive scale, hardware failure isn't some possibility you plan for. It is a daily, operational certainty. Relying on one super powerful machine is like putting all your eggs in a basket that you know for a fact is going to break. And that realization, it changes everything. So if one giant computer is a non-starter, what's the answer? Well, the solution is actually beautiful in its simplicity. Don't use one machine, use thousands of regular off-the-shelf computers all working together. This is the whole idea behind distributed computing. The very first step is to completely rethink how we store the data. Instead of having one massive file on one giant hard drive, a distributed file system, or DFS, comes in and chops that file up into smaller, manageable chunks. Then, to protect against those daily hardware failures we were just talking about, it makes multiple copies of every single chunk and scatters them across different machines all over the network. And this approach, it gives us three huge wins. First, it's scalable. As your data grows, you just add more cheap machines to the cluster. Easy. Second, it's fault-tolerant. A computer can literally catch fire and your data is still safe. But the real game changer, the crucial advantage, is data locality. We bring the computer program to the data, not the other way around. This avoids the insane bottleneck of trying to move petabytes of data across a network.
Okay, great. We've solved the storage problem. The data is distributed, it's safe. But how do we actually do anything with it? How do you ask one question and get an answer from thousands of different machines? Well, this is where the MapReduce paradigm comes into play.
Let's use an analogy here to make this crystal clear. Imagine trying to count every single word in a library. It would take one person basically forever. But what if you gave one chapter to each person in a huge group? That initial counting phase would get done way, way faster. And that, right there, is the divide and conquer idea behind MapReduce. The whole process really boils down to two key stages. The map phase is where every computer works on its own little piece of the puzzle in parallel. That's like each person counting the words in their own chapter. Then the reduce phase is where all those individual results get collected and summarized to give you that one final answer. So here's the entire workflow from start to finish. First, all the map tasks run at the same time. Then, and this is a really critical step in the middle called shuffle and sort, the system gathers up all those partial results and groups them together. So all the counts for the word war from every single chapter end up in one place. And finally, the reduce tasks just add up the counts for each word to get the grand total.
Okay, so this is awesome. We've figured out how to process these enormous datasets in parallel. But we've just created another massive problem for ourselves, the cost. We're talking about the cost of disk space to store petabytes of data and the cost of the network bandwidth to move it all around. How on earth do we manage that?
The answer, of course, is that we make the data smaller. This is the magic of data compression, a technology that is, and I mean this, absolutely fundamental to how our modern world even operates. I mean, really think about it for a second. Without compression, streaming a movie would be impossible. Your cell phone's data plan would be astronomically expensive. Web pages would take forever to load. Compression isn't just some neat technical trick, it's the invisible engine that makes the digital services we use every single day even possible.
So, how does it actually work? How do you just take a file and make it smaller?
Well, there are two main strategies, and they each have a very different philosophy behind them.
It all comes down to one critical trade-off. Lossless compression is like a perfect vacuum seal. When you decompress the file, you get back exactly, bit for bit, what you started with. This is absolutely essential for things like text or computer code, where changing even one bit is a total disaster.
Lossy compression, on the other hand, strategically throws away bits of information that our human senses probably won't even miss. It's the reason a photo or a song file can be so much smaller, but it also means you can never get back to that original, perfect quality.
So let's check out a really clever lossless technique. Huffman compression is all about playing the odds. It looks at a file and notices that some characters, like the letter E in an English text, show up way more often than others, like Z or Q. So it builds a custom code where E gets a really short binary sequence and Z gets a much longer one. And over a big file, that adds up to a huge amount of saved space.
Now, a completely different lossless approach is the LZW algorithm. Instead of analyzing the whole file up front, LZW is dynamic. It actually reads through the data and builds a dictionary of repeating patterns as it goes along.
So check out how this works. The first time the algorithm sees the pattern AB, it adds it to its little dictionary with a new code, let's say 256. Now the next time it sees AB, it doesn't have to send the codes for A and B again. It just sends that one single code, 256. It's constantly learning and swapping out longer patterns for shorter codes.
And the power of this is just crystal clear. That original 11-character string gets squashed down into a sequence of just 6 codes. We've nearly cut the data size in half just by spotting and replacing those repeated patterns. It's brilliant. So after diving into parallel processing and data compression, what's the big picture idea we should really walk away with? Well, first, let's just remember the scale we're talking about here. The web alone is estimated to have something like 50 billion pages. The challenge isn't just big, it's almost impossible to comprehend, and it is growing every single second.
Our ability to manage this digital explosion really rests on 2 foundational pillars. Number 1, we parallelize. We spread the work out, dividing massive problems among thousands of machines. And number 2, we compress. We use clever algorithms to shrink the problem, making it cheaper to store and faster to move.
And this is the final thought I really want to leave you with. These are not just abstract, nerdy computer science concepts. Every single time you type something into a search engine, you are kicking off a massive MapReduce job. Every time you stream a video, you're benefiting from decades of research into compression. These 2 pillars are constantly working right behind the scenes to power your digital world.
If this helped you understand the invisible backbone of our digital world, we'd really appreciate it if you'd like, share, and subscribe for more explainers. Thanks for watching.